Last time, Mr. Hazard found the speed of sound. This time, I'll find something 6 orders of magnitude larger. The speed of light.
It's the week after Easter, and that means homes all across America are overflowing with stale Peeps. Now, you could either eat those Peeps, or you could use them to find the speed of light.
Finding speed of light with Peeps.
The speed of light is one of those numbers that people have chased for centuries. Galileo wanted to know how fast light moves,
Buonasera.
so he proposed an experiment.
Facciamolo.
He would uncover a lantern, and when the light reached his assistant, the assistant would quickly uncover his own lantern. Using a water clock, Galileo would keep track of the time between uncovering his light and seeing his assistant's light. Up close, there was no noticeable delay except for the split second it took his assistant to react. Then they started moving away from each other. Galileo figured the delay would get longer and longer because the light would need more time to travel the greater distance. But even when they were a mile apart, there wasn't a noticeable pause.
Che rabbia.
He couldn't have guessed that light had made that trip in 100,000th of a second. Centuries later, in 1849, a French scientist, whose name I can't pronounce,
Armand Hippolyte Louis Fizeau.
came up with an even better way to measure the speed of light, which was pretty impressive considering that people weren't even using light bulbs yet. He took a toothed wheel and spun it faster and faster. He shot a beam of light between the teeth and reflected that beam of light off a mere 5 miles away. By the time the light got back, a tiny fraction of a second later, the teeth had moved over just enough to block the light. No light made it back through. But if he made the wheel spin a little faster, the teeth would move over one whole position and the light could get through. So when
Fizeau.
saw the light, he knew the wheel was spinning so fast that a single tooth was moving over one place in the time it took light to travel 10 miles. With some quick math,
Armand Hippolyte Louis Fizeau.
determined that the speed of light was 700 million miles per hour, which we now know was only 5% off the actual value. Today, I can find the speed of light in my kitchen, and that brings us back to Peeps
Finding speed of light with Peeps.
and a microwave,
And a microwave.
and just a little bit of physics.
And physics. Just a little bit.
Microwaves travel at the speed of light. And like all waves, their speed is determined by how fast they go up and down, that's the frequency, and their wavelength. The frequency is written on the side of my microwave right here, 2,450 megahertz. So we've got the frequency. Now to calculate the speed, we just need to know the wavelength. And we can find the wavelength by microwaving Peeps. I'll set it on low so the Peeps don't just explode. And let it run for a minute or two. Inside, microwaves are bouncing around. In some spots, there isn't much energy at all, and the Peeps in those areas stay cold. In other spots, there's lots of energy, and the Peeps get really hot. Those hot spots are half a wavelength apart. So, in theory, if I measure the distance between melted Peeps, I can find the wavelength. And sure enough, some of the Peeps are really gooey, while others haven't melted at all. Poking around, I found a rough location for a handful of hot spots, and I measured the distance between them. Those average out to 2.43 inches, so that's half a wavelength. Multiply by 2, and we get a wavelength of 4.86 inches. So now,
So I went out and bought a bunch of Peeps, put them into a glass dish, and popped them into the microwave. My microwave has a frequency of 2,450 megahertz. It's important to remove the plate so that when we put the Peeps in, they don't rotate. We want them to stay still. So I popped the Peeps in, set the microwave on low power for a couple of minutes. I think I put on 3 minutes, and I hit start.
So when I took the peeps out, I put some toothpicks in where I thought they had melted. It was really kind of hard to figure out exactly where they melted and to see if I missed a melted spot. So I came up with another idea. I cooked an egg, just the egg white, on low power. And when you take it out, you can see there are distinct spots which are cooked and those which are not. And the ones that are cooked correspond to the antinodes of the microwaves. And when I measured the distance between the cooked parts of the egg, they all seem to be about 7 centimeters apart, roughly. So doing a little bit of math, remember that the frequency that the microwave told me the magnetron puts out its waves at is 2,450 megahertz. We'll need to convert that into hertz, so we'll do a little factor label. 10 to the 6 hertz is a megahertz. And so this comes out to be 2.45 times 10 to the 9 hertz. Also, to find the wavelength, remember that what we measured was actually half a wavelength from one antinode to the next antinode. So to get the full wavelength, I'll multiply by 2, so 14 centimeters instead of 7 centimeters. And again, I want to work in fundamental SI units, so I'm going to convert this to meters, and that's 0.14 meter. Now I can use the wave speed equation, v equals f lambda, plug in my numbers, and I get 3.43 times 10 to the 8 meters per second for the speed of light. This isn't bad, it's 14% higher than the actual speed of light, which is 3.00 times 10 to the 8 meters per second. So after the success of the egg to find the speed of light, I decided I'd try to get it even more accurate by putting a paper plate with nothing on it in the microwave. Not a good idea. I thought I could burn holes and measure the distance between the holes, but a microwave cooks water, and if there's no water, there's nowhere for that energy to go, and my microwave broke. So I'm on Home Depot right now looking for a new microwave.
Science is a little harder than it looks, isn't it, Mr. Pecor? If you need to come heat something up, you can come use my microwave.
Oh, it's so big.
Let's take him out.
Oh my god, what happened to our peep?
He's a jumbo peep now. Great.